Hi, everybody. Welcome back. So last time we talked about gate teleportation, which was a way that we can basically perform distributed quantum computing tasks between two people. And today we're going to be looking at a special case of it that dealt with the biggest problem that we ran into with gate teleportation, which is the success probability. And this application is known as quantum teleportation. So let's jump into it. So I'll begin by sharing my screen as usual. And so recall with gate teleportation, what the idea behind it was that imagine some kind of a game where you've got Alice and you've got Bob. They're initially in the same lab together. But Bob's just accepted a new position at a university, and so he'll be leaving the lab. And ultimately, what they'd like to be able to do is Alice would like to send a state to Bob and apply a particular gate to it. So the basic idea behind the protocol is that while Alice and Bob are together, they begin by preparing the following quantum state. This state is a state that we call phi plus, which is 1 over root 2 to the n, sum from j equals 0 to 2 to the n minus 1, j tensor j. So this state has the following property, right? If Alice were to measure her register, like imagine this is Alice's register and this is Bob's register. If Alice measured her register and got an outcome of 5, then Bob, if he measured his register, he would get an outcome of 5 too. These two registers are perfectly correlated. And this state is known to be what's called an entangled state, which means that we cannot write it as a tensor product of two other states. So that is that's a state that they begin with. Then what they do is they apply the transformation identity tensor U acting on phi plus, where, just to be clear, this unitary is acting on Bob's space. Then what they do is Bob takes his half of the share and then he leaves to go to a different lab. So now that they're in different labs, Alice can't send quantum information to Bob. But she can still send ordinary information because, they still got the internet and stuff. So the idea basically behind this is that what Alice does is she prepares her state, psi, that she wants to send to Bob with this operation U that they've kind of pre-cached and stored in their entangled state. Then she has, between the two of them, they share an entangled state, identity tensor U, phi plus. And so then if Alice is capable of applying a projection onto this state, and onto the state psi phi plus, where this part over here is Alice's space and this is Bob's space. So just to be clear, this phi plus register spans so it spans only Alice's information and half of the qubits on the entangled state between them, i.e. this touches that part of phi plus, but not the B part of phi plus. Okay, so if we do that, then we found with probability 1 over 2 to the 2n, Bob receives the state U acting on psi. And so Alice can call Bob because she's the one who applies this projection. And she can tell him whether or not the projection works. And tells him that he's good to go on his part of the processing. So yeah, basically, he's got now, if Alice ends up successfully applying a projector onto the state 5+, she can tell him that it worked. And then instantly, Bob knows that he has the correct quantum state and can begin to work off of it. This is something actually was initially very weird, because basically what this distance between Alice and Bob can be arbitrary. So what ends up happening in the protocol is that when Alice ends up measuring her state, and if she succeeds, then immediately the state that Alice knows Bob has on the other side ends up becoming U psi. And this created some problems for folks like Einstein, who actually initially studied this in the famous EPR, or Einstein-Podolsky-Rosen paper. That basically, it seemed like the universe essentially was, in some sense, transmitting information faster than the speed of light between the two. It turns out that there's no way that you can use this effect in order to usefully transmit information, in part because the success probability is so small. And in order for Bob to be able to usefully use his state, Alice has to tell him that it worked. But nonetheless, it is kind of a strange aspect of quantum mechanics that you end up having these updates that seem to be non-local. Of course, similar things also happen with classical probability theory, unsurprisingly. So that is how gate teleportation ends up working. Now, the big problem, as I mentioned before, is this awful success probability. So the question is, can we get around this? And the way that we get around this is by using teleportation, or by focusing our attention on a subset of gate teleportation protocols. Simplest one is just teleportation. And in this case, what we want to do is we want to do gate teleportation with the unitary being the identity gate. So in this particular context, we've got Alice and we've got Bob. And Alice just simply wants to send a quantum state over to Bob. Okay? And it turns out that for this task, we actually can succeed in this with probability 1. So in order to see let's go through and take a look at the analysis. The basic idea behind it is that in this case, the transformations are so simple that we can figure out what happens when the projector fails. And on those cases, when the projector onto the state phi plus fails, we correct. And because we can do a cheap correction to the quantum state whenever any failure ends up happening, effectively, the probability of success becomes 100%. So to see how this works specifically, first thing I want to remind you of is how we can go about computing or implementing a projector. There's a couple of different ways. The first method is the Hadamard test, but the second and most straightforward way in this application is by doing a basis transformation. So recall that if we had a state 0, 0 coming in, and we applied a Hadamard and then a C0, then going through the algebra, we end up finding that this equals C0 acting on 0, 0 plus 1, 0 over root 2. Now, applying the controlled knot between those two, nothing happens, but controlled knot between these two flips the 1 to a 0. So this ends up creating the state 0, 0 plus 1, 1 over root 2. And so this case over here is just being done for 2 qubits. or trying to teleport one qubit effectively. And so this corresponds to phi plus with n equals 1. All right, cool. So what we have is we have this particular circuit. But what we'd like to do is we'd like to be able to find a way of projecting onto this state. And so we can do that actually by noting that from this circuit, if we started in a state phi plus and then did the opposite of the above circuit, first we C naught and then we Hadamard, we end up getting into a situation where if we measured these two, we will get 0 and 0 with probability 1 in this case. So in effect, what we've done by doing this unpreparation of the preparation circuit is we've walked backwards. We found a circuit that will tell us whether or not the state is phi plus coming in. And then if we wanted to make this a true projector, what we would do is we would take the quantum bits, which upon success would be 0 and 0, coming out here, and then we would re-prepare phi plus from it, which we could do, again, by the opposite. However, this part of the circuit, for our purposes, is irrelevant. We don't actually care about the residual quantum state that Alice will have after performing her measurements on her side. So this part over here for applying a projector is kind of not needed. So we're going to drop this part of it in our discussion today and only use this as our way of kind of doing a poor man's version of a projector. So that is the teleportation, that's how we can apply projection. And this projection will work if both of the qubits are measured to be 0. Okay, cool. So recall that what we wanted to do with gate teleportation is we wanted to apply phi plus, tensor phi plus, tensor identity on a state psi that Alice has and a state phi plus shared by Alice and Bob. Okay. Now, in this case, phi plus is just going to be, or I should say, identity tensor U acting on phi plus. In this case, U, or the unitary that we want to teleport, is just the identity. Because all we want to do is move the state. We don't really want to modify its value. So without loss of generality then, for this particular application of gate teleportation, I can remove that term because it's just identity, tensor identity. All right, and so this projection, we can non-deterministically implement by carrying out the process that I mentioned before. We start with state psi, and Alice and Bob share the phi plus state on those two quantum bits. Now, then what we do is we do the inverse basis transformation. We do a C naught down here, and we apply a Hadamard. And in the event that these are measured to be 0, we argued previously that that's equivalent to applying the projector onto phi plus. Okay, so if 0, 0, then teleported. But we didn't argue based on the previous stuff, what happens when it fails? So what happens if you were to measure 1, 0 instead of 0, 0? Then we'll see here next that measuring that result doesn't actually destroy the important quantum information. So let's go through and do that analysis. So to begin with, I'm going to assume that Alice is sending in a single qubit state that without loss of generality is A0 plus B1. Okay. And so the initial state that Alice and Bob share to begin with will be A0 plus B1 on Alice's side, tensor 0 Alice, 0 Bob, plus 1 Alice, 1 Bob. And what I've done here is I put the A and the B's as subscripts of these, just to be clear which of the two people in the protocol has each of these individual quantum bits. So the first two are owned by Alice, and the last one is owned by Bob. Now, what we do is we now are going to go through and apply the controlled NOT gate and the Hadamard. Recall that Hadamard maps 0 to 1 over root 2, 0 plus 1, and 1 to 1 over root 2, 0 minus 1. So very first thing that we can do is we can group these all together and do this controlled NOT operation. So using the distributive property of tensor products, we can treat this as A 0, 0, 0 plus A 0, 1, 1. And that's just the tensor product between here and there, respectively. And then B1, 0, 0 plus B1, 1, 1. Okay, now we do a controlled NOT operation. It doesn't do anything for the first two terms, but it actually will end up messing up or changing the last two. It'll create 1, 1, 0 and 1, 0, 1, because the control NOT is between the first and the second, or the leftmost and the center qubit, using this kind of standard correspondence between them. So now we have this particular quantum state. All that we need to do is just apply a Hadamard transform to it. And we can just use these rules over here to break it down. I'll skip the substitutions for you. After just going through these substitutions and regrouping stuff, we end up getting something of the form 0, 0, tensor A0 plus B1 plus 0, 1, A1 plus B0. And then we get plus 1, 0, A0 minus B1. And finally, we get the most screwed up of all possible states here, A1 minus B0. Oh, and this is all divided by 2. Okay, cool. So this is the resulting state that we end up getting when we teleport. Now, you can see immediately that if we measure the first qubit and we get 0, 0, then we project onto this state. And that state will be of the form 0, 0 tensor, the correct state, psi. So if we measure 0, 0, then Bob will have received the state psi. However, in the event that you end up measuring, say, 0, 1, or Alice ends up measuring 0, 1, then the state that Bob receives is something a little bit different. Bob receives A1 plus B0. Now, in the event that 1, 0 is measured, Bob ends up receiving A0 minus B1. So you can see, actually, that there's kind of a bit of a pattern here to it. This state is actually not acting on psi. This state over here is Z acting on psi. And this maximally messed up state over here is not acting on Z psi. Okay, so what this is saying actually is that when teleportation fails, there's three options that we can have. We can have that Bob receives a state that has an X gate applied to it. Bob receives a state that has a Z gate applied to it. Or Bob receives a state that has both the X and the Z gate applied to it. Now, if Bob receives this state and he knows what X and Z are, or sorry, which type of error Alice observes when she measures, because again, recall that this measurement is completely under Alice's control. Bob does not do the measurement. And so what has to happen is that in these cases, Alice will call up Bob over like an old-timey telephone and send that information down to Bob. So for example, if she measured 1-1, which is the worst case possible, she'd call up Bob and say, yeah, Bob, those measurements, they screwed up as bad as they could. It's a 1-1. So how about you fix that by applying a Z to your qubit and then an X to your qubit? And so there's a way that we can describe this type of algorithm within the graphical calculus that we use for the following. And basically, inside the circuit model, we will often use double lines to denote classical information coming out of it. So there's two different cases. Actually, there's two different cases that we want to do. The second qubit, if it's 1, note that that corresponds to an X error. And the first qubit at the top corresponds to a Z error. So what we want to do is we want to do the following. Let me just make sure that I've got this right. Okay, so what we want to do is we want to be able to fix this by applying first a NOT gate and then a Z gate. So we can do that by doing the following: X, Z, where this means if 1 is measured, apply Z. Okay. And so then that is the circuit. We can see that in all 4 cases that we get down here, the resulting state will always be psi popping out the other side with this protocol. So this means that Bob gets psi with probability 1. All right. And so that is how quantum teleportation ends up working in a nutshell for sending just 1 quantum bit. But I get the question is, how about doing this in general? So in general, Alice and Bob could have a massive entangled quantum state that they want to be able to send towards each other. The question is there some way of reducing that problem of sending the quantum state between the two into a series of teleportations? And the answer is, yeah, there really is. All you have to do is teleport each of the bits individually. Now, I don't know about you, but when I first saw this, I didn't really feel that that this was all that intuitive, actually, because quantum entanglement is weird, and wasn't clear to me that teleporting the bits one at a time actually works. So let me take you through the argument showing that you can teleport a complicated quantum state, specifically a pure state for you quantum nerds, between Alice and Bob. And the basic idea behind this this protocol is, let's just begin by looking at case one. Assume that the state that they want to communicate is actually just a product state. It's of the form psi1 tensor psi n. And each of these is going to be one qubit. So it's in order to see how this this ends up working, it's really useful to also invoke this notion called the principle of deferred measurement. And the basic idea is that what the principle of deferred measurement ends up saying is the following, at least in our context. It says that if we begin with the state psi, and we have some kind of a circuit over here, and we Hadamard, and we well, let's give me a little more space here, and measure, and phi plus, of course, was fed in over here. Now, if we end up having a state x classical z over here, then actually there's a way that we could rewrite this. We could say, well, this measurement over here, if we measured and got a 1, then the resulting state that we're going to get will be the state that is consistent with this value being 1. And similarly, if we measure the top one to be 1, then this state over here will be consistent with being plus 1. So what that means is that we can write this circuit equivalently as the following. We apply Hadamard, and we then do a controlled X going down here, and a controlled Z going here, and then we measure after we've done the corrections. In this case, the order that we do them is totally irrelevant. They end up providing exactly the same quantum state down at the bottom. Well, the reason why this is really useful as an argument technique is because of the fact that it's difficult to track through all of the possibilities that we end up getting with the measurements. And by delaying the measurements until the end of the protocol, what we can do is we can actually just stay 100% inside the quantum formalism without having to break everything down into a large series of cases corresponding to the exponentially many outcomes that we can get in the n qubit version. And the reason why I say exponentially is because for every qubit that we want to be able to teleport, there's 4 specific measurements. So the total number of measurement outcomes that we could get for this would be 4 to the n. Okay, cool. So if we have this, then let me define this circuit modulo the measurement over here to be a circuit that I'll call UT for U teleportation. All right, so then the initial state that the way the protocol is going to work is we're going to have psi1 fed in with a copy of phi plus over here. And we'll throw that into UT. Then we'll get psi2 with another copy of phi plus down here, feed that into UT, going all the way down. And then UT will always output psi1 over here and psi1 over there. Now to see it, we can actually just go through our original circuit. We notice that before measurement, our quantum state was this guy over here. So if we end up applying the correction operations, let me just copy this. So if we end up copying, oh, that was interesting. Okay. Wow. All right. Windows is clearly being too smart for its own good. Okay. So if we've got this particular state and we go through and do the correction operations we see above on it, i.e. the controlled NOT and the controlled Z, what we end up getting for each of these individual qubits is we get 1/2 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, all tensored with psi. Okay, which is equivalent to saying that if we do these if we could quantumly do these correction operations between Alice and Bob's lab, of course, we're not doing it, we're just using this as an argument technique, then Alice and Bob, or Bob's state would be psi as intended. So if we do that, then we can see that this quantum circuit over here is going to carry, here it's going to be 1/2 0, 0 plus 1, 1 over there. And this one is going to be exactly the same. So if we do this to each of our qubits, we're going to get a quantum state that is going to be of the form 1/1/2 0, 0 plus 1, 1 psi 1 tensor 1/2 0, 0 plus 1, 1 psi n for each of the n copies of the circuit that we've applied. Now, when we go through it and rearrange the definitions of the spaces here, we can see that this quantum state is equivalent to 1/2 to the n 0, 0 plus 1, 1 tensor n tensor psi. So this means from the principle of deferred measurement, if we changed our circuit to allow controlled NOT gates between Alice's qubits and Bob's qubits, then we can implement this unitary, which we see does the following. But this is equal to the version where the measurement actually occurs. So therefore, when we take a look at the version where each of these is measured, and we apply the correction operation down here, the resulting quantum state that we get out will be exactly the same. It will have teleported the state psi from Alice to Bob. Okay, so that is the first of the two cases that we have to take a look at. So we know from this that if we have any state j over here, which is equal to, say, J0 tensor J1 tensor Jn minus 1, then applying this teleportation circuit UT to each qubit will teleport J. So now, what if the state that Alice wants to send to Bob is much more complicated? What if it's of the form sum over J, AJ, J? Well, if we carry that out, then we end up with something actually that ends up looking very similar. We can re-express this circuit. We'll if we carry out the exact same circuit, UT, where this is, let's call it psi1, that's this bit over here. Maybe I should have called it 0, but and we've got phi plus here going all the way down to feeding in psi n and another copy of phi plus there. Then what we can see is that we can rewrite this teleportation protocol where we're teleporting each of the bits sequentially as the following. We can rewrite this as being sum over j, aj, j, tensor phi plus to the n, where these are just the extra copies of the phi plus state that we're keeping around in order to be able to send the information through the teleportation protocol. Okay, cool. So now we're applying on this UT tensor n is an n parallel copies of the teleportation circuit. Now, because quantum mechanics is linear, this is just sum over j, a sub j, u sub t, tensor n, acting on now j, which I'm going to rewrite as j0, tensor phi plus, j1, tensor phi plus. And we argued already that this was the sum over j, 1 over 2 to the n, 0, 0, plus so on and so forth, 1, 1, tensor n, acting on the remaining state, which is just going to be j naught tensor j n minus 1. Now I've played, again, just like before, I've played a little bit of games in terms of moving around the locations of where the j's and the phi pluses are in the tensor products over here. The two are logically equivalent and don't change anything. But just I wanted to note, if any of you are getting confused about where different tensor products are specifically located, just for convenience, I've permuted the resulting matrices, or equivalently just flip the labels of some of these spaces that we have in here, just to make the result more readable. Now that we have this, we end up seeing, oh, well, actually, because this is a constant over here, we can actually move that outside the sum. So this is sum over j, aj, j, which is, of course, no, actually, I need to keep that in here, plus 1, 1, tensor n, sum over j, aj, ajj. And this state over here is what we define to be psi. So there we have it. In general, teleporting each of these individual qubits is equivalent to teleporting the entire state, even if that state is crazily entangled. So that is teleportation in a nutshell, and it's a really, really important technique. So to give you a concrete idea of places where teleportation ends up showing up is, at present, what we have, one of the major technologies that's used in quantum computing is ion trap quantum computers. I won't go into any details about the physics, but the basic idea behind these ion trap quantum computers is that they store information in hyperfine states of atoms inside chains, and basically the idea is that we have all of these individual traps that are often kind of like, you can envision them as being like set up inside a lattice of different control and interaction regions. And they have to be set up like this because in practice, we can only control a limited number of ions inside each trap. And, the number of ions that we can really be able to control inside some trap, it varies, but it's definitely less than 50 inside each of these different segments. And so the idea basically is that what if you want to take, say, 2 quantum bits and over here and interact them with those ones? Well, the easiest way to do this is to actually use quantum teleportation in order to be able to move that information over. And the way that they practically end up doing this is that they will use light and entangled light in order to be able to perform teleportation between these two without ever having to actually physically move the ions around. Because if we move them, it turns out, through this, there ends up getting to be a large amount of motional heating that ends up happening. So it's a lot better if you can avoid it to just rely on teleportation to be able to move your ions around an ion trap. So it's basically, teleportation is probably the best way that we have for moving information around. Another thing that that it often gets a lot of use in is something known as entanglement swapping. So imagine that what we have is we have a network of individual sites, each of which we can envision is like a distributed quantum computer. Now we've got Alice and Bob on 2 different sides, and they'd like to be able to share a quantum state with each other. But unfortunately, they've only got direct links between other nodes. The entanglement swapping protocol, how this ends up working is basically what ends up happening is that Alice begins by forming an entangled pair between her and the first repeater. These two end up forming an entangled pair, consuming that and basically teleporting it through, and then teleporting it through again. And so then by the time we end up going through all of this, Alice has effectively, only using nearest neighbor swaps, sent half of her entangled pair to Bob. And now Bob can, through this chain of teleportations, use that information to have kind of a shared 5+ state between her and Bob that they can use to be able to send a quantum state directly across. And this is very important in quantum networking because it's really unlikely in quantum networks that Alice and Bob are actually going to have a direct link to each other. It's much more likely that they'll have to go through intermediaries, and this process of teleportation allows them to do that. So that's teleportation in a nutshell, and hope you liked it. And it's surprisingly simple, everything considered. So thanks a lot. Now, next time, we're going to be taking a dive back in to the universality claim. I'll be proving to you, finally, that that single qubit unitaries and controlled knot operations are universal for quantum computing. And then with that, you kind of have a big picture, I feel, of most of the key parts. Once we have that, we're going to be moving on to query complexity and kind of looking at deeper theoretical aspects of quantum computing. Thank you very much, and hope you enjoy.